Okay, so in this particular lecture, we are gonna start with the concepts of metric spaces. Okay, this lecture onwards, we will keep on discussing metric spaces, and this lecture is going to be pretty long and detailed. So please keep your focus and be patient with whatever I'm gonna do in this particular lecture. Before studying the concept of metric spaces, I need you people to know what are vector spaces. What are vector spaces? What is an inner product space? What is an inner product space, and what is the norm of a vector. Okay, so before moving on to the concept of metric spaces, let us just discuss a few elementary concepts about vector spaces, inner product spaces, and so vector spaces. So a set V over a field F is a field, okay, is a vector space, we denote it like this: V, we denote it like this: V over F is a vector space if V with respect to some operation, the first operation which is there in the field, the concept of the field, that operation, the first operation is an abelian group, and for all alphas belonging to the field, these are treated as scalars. Any element from the field is considered a scalar, and elements from the set V are treated as vectors. Okay, so for all scalars in F and vectors in V, alpha times V is contained in V. Alpha plus beta times V, which is equals to alpha times V plus beta times V. These dot operations are not mandatory to be multiplication in the sense. See, this F is a field, right? Giving a very elementary concept. So this F is a field, right? This F, let me change the color. So this F is a field with respect to some operations, right? So this operation is this one, this dot operation is this dot operation. If you know the concepts of fields, then we know that these symbols plus and dot, they are not our algebraic additions and algebraic multiplications. They are just used to denote a first operation and a second operation. Okay, so here this dot and this plus symbol, they only refer to certain operations which we have considered for F to be a field, and the operations are being used here to recognize V becoming a vector space. Okay, so alpha plus B dot V equals to alpha dot V plus beta dot V, and alpha times V plus U, or alpha dot B V plus U, is equals to alpha dot V plus alpha dot U. V dot 1 is equals to V. 1 is the multiplicative identity of the field, and alpha dot beta dot V is same as alpha dot beta dot V, and these happen for all VU belonging to the vector V, vector space V, and alpha beta belonging to the field. So if there exists a set V over some field F which obeys these conditions, that V with respect to the first operation is a abelian group, and with respect to second operation obeys these conditions, then we say that V is a vector space over F. This is a very elementary. Now, using the concept of vector spaces itself, we define one more thing which we call the inner product space. Okay, an inner product space. Very basic thing. Let's just understand. So we define this as a function. We define this as a function from V cross V to the field F, where V over F is a vector space. Okay, so we take a vector space V which is over this field F. We have a mapping from V cross V to F such that it obeys the following condition. Point number one, UV under the mapping equals to the conjugate of VU. Number two, UU mapping of UU is always greater than equals to 0, and the mapping equals 0 if and only if U is a 0 vector. This is called the concept of positive definiteness. Positive definiteness. Clear? Point number 3. U plus V with W under the mapping equals to U with W plus V with W. Okay? All these elements are from the vector space V. And number 4. AU with some V equals A times U. Okay? Number 5. There is one more point, okay, which is U with AV equals to A conjugate U. So this is a direct result of this point and this particular point, because you know what happens here is that, so this can be written as AV with U and its conjugate. So if we take the A outside, it comes out as a conjugate VU, and then we can write it as this. Pretty simple. That's why I gave a star here, because it is sort of a resultant. So these four conditions are what a certain function from V cross V to F must follow. Then the function can be called an inner product. The function can be called an inner product. Rather, is called an inner product. Okay. And if V over F is a vector space such that there exists an inner product from V cross V to F, okay, then V over F is said to be an inner product space. Okay, an inner product space. So this is the main concept. So basically, you have a vector space, and the vector space is such that if you find a mapping like this from V cross V to F such that it obeys these four conditions, then the mapping is called an inner product. And such a vector space which has this sort of a function definition, the vector space is called an inner product space. Okay? That is this definition of an inner product space. Okay, and understanding the definition of inner product space, we move on to our next topic, which is called the norm of a vector. It is called the norm of a vector. Okay, so norm of a vector basically is sort of, it is defined like this. So let V be an inner product space. Let us have an inner product space V. So let V be an inner product space. Inner product space for any element of V. The norm, or basically in simple words, it's the length of the vector. Now if we consider a plane or a region where this vector is contained, you might say that the distance between the origin and the end point of the vector, you might say the length of the vector. the norm or length of V, this element, is defined as the norm of V, and this norm of V is mathematically represented as the root over of the inner product of V with itself. Okay, V with itself. So this is the definition of the norm of a vector. Clear? So since this norm of a vector is, in simple words, it's a inner product itself, so it will obey all the conditions of an inner product. So so the basic three conditions which we need to find the norm, or which the norm must obey, are, so the properties, rather, you might say the properties of norm are, you may say, the first point is the norm of a vector is always greater than equals to 0, and the norm of a vector equals to 0 if and only if the vector is a 0 vector. Okay, point number 2, any scalar multiple taken of a vector, its norm is given as the scalar multiple times the norm of the vector. And the third point, and the most important point, is the triangle inequality. We have studied the triangle inequality as a mod function in case of the real numbers, right? So in case of the real numbers, the norm function is basically given as the mod function, as simple as that. Okay, in case of the real numbers, we have the norm function as a mod function. Okay, but what happens in that particular case, or rather, let us first define the concept of triangle inequality with respect to norm, and then we will be, kind of seeing what the triangle inequality which we have studied on. So in case of the norm function, the triangle inequality is given as norm of x plus y is less than equals to norm of x plus norm of y. Okay, we have already studied this particular thing, as we already know. One second, just take this red color. So we already know this. The mod of x plus y, it's very thick, is always less than equals to norm of x plus, mod of x plus y is less than equals to mod of x plus mod of y. Okay. We also know one thing, that mod of x is always greater than equals to 0, and mod of x equals to 0 if and only if x equals to 0, and also mod of some multiple of x is same as a times the mod of x. Okay, so can we say that the mod function is basically a norm? Yeah, we can obviously say that. Okay, so we have studied this concept in case of real numbers, right? Real numbers, complex numbers also. Okay, so in case of, we can say that in case of real numbers and in case of complex numbers, this norm can be given as the mod of any element taken from the particular set. Basically, these are vector spaces, and these are inner product spaces. Okay, got it. We will be coming to these things. And one more definition which we need to see before moving into the concept of metric spaces. What is a normed linear space? What is a normed linear space? One more thing, can we define norm as a function? Can we define norm as a function? Obviously, we can define norm as a function. You can define norm as a function from the vector space to its field. Okay, so you can do it in case of real numbers as norm of x is basically the mod of x. Clear? Got it? Okay. these are pretty simple definitions. Let us understand what is a non-linear space. What is a non-linear space? So, so suppose we have a vector space. Let's say V. So let V be a vector space. Okay, and we define norm. We define a norm from the vector space to its field such that norm of V equals to the square root of the inner product of V with itself for all V belonging to the vector space V. Okay, so if such a function exists in a vector space V, if such a function exists in a vector space V, then so if such a definition if such a definition exists in a vector space as given to be V, it is called a normed linear space. The vector space is called a normed linear space. Basically, if there exists a norm function, or if there exists the definition of a norm in a vector space, we call the vector space to be a normed linear space. Okay, is this much clear? Okay, so now we move on to the concept of what is a metric space. Let's see what is a metric space. Yeah, it's pretty simple to understand the concept of a metric space. Nothing much complex, but you need to hear and go by each of the lectures. Then you will be better understanding. Okay. So if we speak about a metric space in very simple words, then a metric space is a set in which we can talk about the distance between two of its elements, in which we can talk about the distance between two of its. Is it clear? Got it. So now going by the mathematical definition, we might say it like this. So a set X with respect to a function D is called a metric space if D, which is a function from x cross x to R, obeys the following conditions. Point number 1, D of xy is greater than equals to 0 for all xy belonging to the set X, and D of xy equals 0 if and only if x equals. Point number 2, D of xy is equals to D of yx for all xy belonging to the set X. And point number 3, D of xz is always less than equals to D of xy plus D of yz for all x, y, z belonging to the set X. Okay, and this is what it seems to be is the triangle inequality. Okay, Got it? Now the thing what we need to speak about here is that these properties kind of resemble the definition of a norm. You can check the properties which the norm function obeys, and you might find some similarity between these three properties and the properties which the norm used to. Okay, let us move on to the properties of a norm. Okay, or rather, I had done it here only, right? Yeah, properties of norm. So norm of v must be greater than or equal to 0 and equals 0 if and only if it's a 0 vector. Scalar multiple comes out and it obeys the triangle inequality. Okay, so 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 is this much done, right? So suppose we move on to the next page. So now how can we relate, or how is rather a normed linear space related to a metric space? We need to see it carefully. So normed linear space with metric space. So I have already defined what the normed linear space is. Okay. So suppose X is a vector space you have taken, or rather X is a set. Let's say X is a set. Maximum of these concepts are related to vector spaces. So these sets are vector spaces. Okay. These sets are vector spaces which we define as a metric space. Okay. So X is a vector space, and we define the norm function from X to R, and we know it obeys three conditions. I'm writing them again. So norm of X is greater than or equals to 0 for all the elements belonging to X, and the norm equals 0 if and only if X is a 0 vector. X is a 0 vector. Property number 2, scalar multiple comes outside. Okay, for all elements belonging to X. And property number 3, which is the triangle inequality. Norm of X plus Y is less than or equals to norm of X plus norm of Y. And I have given you a very simple example. You can define norm from R to R as the mod function. Now we observed that every normed linear space is a metric space. Every normed linear space is a metric space. Considering the definition of the metric, this function, that function d, is called the metric. In a metric space, the function is called the metric. Considering the metric d of xy as norm of y minus x. Okay, d is the metric, and we say that this metric is induced by the norm, which is defined as given. Is it clear? So we might say that every norm, because this is a very arbitrary definition. So every norm induces a metric. Every norm induces a metric. Converse need not be true. Converse need not be true. We can obviously get a huge number of examples in which you have a metric but it is not induced by any norm. But if you have a normed linear space, or rather if you have a norm, a defined norm, then that norm will obviously induce a metric. Okay. Now some properties related to a metric which we have already discussed, some properties except those ones, is the concept saying that a metric induced by a norm, a metric induced by a norm is invariant under translation, this is called the concept of translational invariance. Okay, this is called translational invariance. Okay, this is called the translational invariance. Okay, so what do we mean by this statement is that I'm giving a very basic geometric explanation. So suppose it is a 2D plane, a 2D xy plane you have, and say this is one point and this is one point. Let this point be x and this point be y, and the distance between them is say d. Okay, now suppose what you do, you shift this point y, symmetrically with x. Okay, you shift this point y symmetrically with x. So suppose say y moves like this upwards, and this is the new point y dash, and the same movement is done by x as, so this is say x dash, and the distance between them will still remain d. The distance between them will still remain d. This is called translational invariance. In other words, you can say that suppose you shift x with x by a and y by a. Okay, so that distance between x plus a and y plus a is same as the distance between x and y. Okay, this is called the concept of translational invariance. And one more observation which we have already got is that a normed linear space implies a metric space. Clear? Clear? Now let us see a few examples. And if we see examples of a non-linear space, we will automatically get examples of a metric space. Okay, so as I was telling to the BSD that while studying in our product spaces and norms, I was not giving examples, so we will take the examples now. Okay, so examples of non-linear spaces which correspond to examples of metric spaces as well. Examples of non-linear spaces. So the first example is the real number. So real numbers with respect to a norm function, which we will define now, is a normed linear space, where the norm of an element of R is given as its modulus. Okay, is given as its modulus. Okay, so from here we can define a metric xy, which is given as mod of y minus x. Similarly, the same thing we can do with complex numbers as well. Okay, it is a normed linear space where the norm of any complex number is given as the modulus of it, and so distance between any two such complex numbers can be obviously taken as the mod of z2 minus the z2. Okay, clear? These two examples are pretty concrete. Now the next example which we are going to taking is going to take half of the lecture. The next example which we are going to take will take half of the lecture. Actually, in this lecture I am not explaining the concepts of the inequalities which are related to norm of a function. Now I'm going to the next page. So there are certain inequalities which are related to norm of a function. Okay, for example, we have the Cauchy-Schwarz inequality. Okay, which imply the proof of the triangle inequality. I am not proving the triangle inequality in this particular lecture. Okay, there are a certain more number of inequalities related to the concepts of norms. Okay, there are some more set of inequalities like the Cauchy inequality. I've just said the triangle inequality. We have some more inequalities we had. I'm not remembering it at this moment. So yeah, we have the Holder's inequality and the Young's inequality. Yeah, Young's inequality and Holder's inequality we are going to prove in this lecture, and we are going to use in this lecture to check what we call the, I am forgetting the name of the particular inequality, Minkowski inequality. So three more inequalities we are going to study in this particular lecture. So I'm just giving you the statement of what we had as the Cauchy-Schwarz inequality. So just you can keep that in mind. So the Cauchy-Schwarz inequality goes by the statement that suppose you have an inner product space, or you can say you have a normed linear space. You see, the basic thing is that if you have a normed linear space, a norm is defined being dependent on an inner product. So a normed linear space must be an inner product space as well. Okay. Suppose you have a normed linear space. So suppose V is a normed linear space. So the inner product of UV, if you take its modulus, it is always less than equals to norm of U times norm of P. This is the Cauchy-Schwarz inequality. And triangle inequality I have already said. Okay. Now basically I fumble around the lecture because I don't prepare these lectures. Okay. These are kind of a result of the previous statements you will see. So these lectures are basically an example, or rather a process, a thought process you might say, a thought process of studying what is being imprinted on this lecture. So let's move on. Yeah. So these things we have understood. Okay. So we have taken two fixed examples of R and of C, and now we are going to define what we call the P norm. What we call the P norm. Okay. So carefully see. This P norm example is quite important. Okay. So as a third example, suppose we take the n-dimensional real number vector space. Okay. So we have the elements as n tuples. Okay. That is any element belonging to Rn comes in the form of n tuples, x1, x2 and so on till x. Okay. Now here we define a number p, a real number p like this. Okay. So it must be, yeah, it can be infinity as well, because we are going to define two cases, one for it being finite and one for it being infinite. So we define what we call a p norm. Okay. So the p norm of x is defined as the summation I equals to 1 to n, the norm of xi, rather we say the mod of xi raised to the power p, and this whole sum raised to the power 1 over p. And this happens if p is a finite number, and if p is infinite, we take the maximum from all the tuples from I equals to 1 to n of all the xi's as a modulus of the xi's. Okay, if p is okay. So this is what we call the p norm of Rn. Okay, this is called the p norms of Rn. Clear? If this was R, that is if n would have been equal to 1, then all these p norms would be same as the modulus of x, which we have already defined as an example. Okay, but if the n is not equals to 2, then we can define p norms. Let's see. So now what we need to prove is that this particular definition of p norm is indeed a norm, or rather I may say that we need to prove that Rn is a normed linear space with respect to this p norm, and then we can obviously say that it is a Minkowski space. because this P norm will induce a pth matrix, P matrix, you might say. Okay, a P norm will induce a P matrix. Okay, so let's see. Now see, the first two properties of the norm, that is the concept of scalar multiple and the concept of it being zero, they are very trivial in this case. Okay, they are very trivial in this case. See, what I'm telling is the concept of norm of x being 0 if and only if x equals to 0, and norm of x, p norm of x is always greater than equals to 0. This property and the alpha property, alpha x equals to alpha times norm of x, these two are very trivial. You can do it on your own. Okay, what we're main concerned about is that proving the triangle inequality. Okay, to prove the triangle inequality, whenever you need to check whether a defined norm or whether a defined function is a norm, the main concern is to prove the triangle inequality. The other two cases more or less become trivial. Okay, triangle inequality. So let us first see what the triangle inequality will look like in case of the P norm. Okay, or rather, let us do one thing. Let us go by cases. Suppose we take the case 1 when P is equals to 1, that is the one norm. It is called the one norm or the first norm. Okay, for P is equals to 1. So for P is equals to 1, norm of x, first norm of x is given as the summation I equals to 1 to n mod of xi. Okay, so we can define norm of x plus y, the first norm of x plus y, as summation I equals to 1 to n mod of xi plus yi. So this can be separated using the definition of modulus, the triangle inequality on modulus. So it is xi plus summation I equals to 1 to n mod of yi, and which is indeed the norm of x, first norm of x plus the first norm of y. Okay, so for p equals to 1, the triangle inequality is pretty much trivial. Okay, in case of the infinity case, we can do it also. In case of infinity, it is also very trivial. Okay, the infinite norm. So in this case, the infinite norm is pretty much written as the norm function itself. Okay. We don't use any suffix. So the norm of x, which was indeed given as maximum of all the tuples in x, right? Mod of the tuples in x. Okay. So norm of x plus y will be given as the maximum I equals to 1 to n of xi plus yi. Again we can separate it. So this is maximum of I plus maximum of y's, which are norm of x plus norm. Okay, so in case of p equals to infinity, it is also very much trivial. So these two cases are done, right? P equal to 1 and p equal to infinity are done. These two are very basic level, norms, or they induce very basic level metrics, which are, kind of an introductory example to metric spaces in almost everything. We are more concerned about the case when p is greater than 1 and less than infinity. Okay, so let's see. So to prove the same for 1 less than p less than infinity, and this is indeed going to take some work. One second. Yeah, so let's see. So what the triangle inequality will look like in this case? So norm of x plus y, the pth norm of x plus y must be less than equals to the pth norm of x plus the pth norm of y. Using the definition of the norm as we have used, we can write this as the summation I equals to 1 to n mod of xi plus yi to the power p whole raised to the power 1 over p is less than equals to summation I equals to 1 to n mod of xi to the power p whole raised to the power 1 over p plus summation I equals to 1 to n mod of yi to the power p whole raised to the power 1 over p. And this inequality is what we call the Minkowski inequality. Minkowski inequality. And to prove the Minkowski inequality, we need to use two more inequalities, which are called the Young's inequality and the Holder's inequality. Okay, so let's see. So before moving on to what the Young's inequality is, we first need to understand the concept of conjugate exponents. The concept of conjugate exponents. Concept of conjugate exponents. Okay, so suppose we take two positive numbers. Okay, let a be a positive number and let b be a positive number. Okay, and say we have a number p. So okay, before defining it, so I was about to define the Young's inequality. Before defining what conjugate exponent is, let us first define what a conjugate exponent is. So p and q are said to be conjugate exponents of each other if for all 1 greater than p greater than less than infinity there exists q following the same conditions such that 1 over p plus 1 over q equals 1. Okay, p and q are called the conjugate exponents. Okay? A very trivial example of two conjugate exponents are p equals to 2 and q equals to 2. This is called the symmetric conjugate exponents. Symmetric conjugate exponents. Okay, and also by convention we take one more such pair of conjugate exponents, which is when p equals to 1 its conjugate exponent is infinity. Okay. Okay, now let us define what the Young's inequality is. Young's inequality. So the Young's inequality is something like this, that suppose we have two positive numbers. The product of them will always be less than equals to a to the power p over p plus b to the power q over q, p and q being conjugate exponents. Clear? P and q being conjugate exponents. Okay, and let us also write the Holder's inequality. We will prove them one by one. The Holder's inequality. It is called the Holder's inequality. Yeah. So let us first define the Holder's inequality using the definition. Then we will pretty easily understand what is the norm for that. So the Holder's inequality says summation I equals to 1 to n mod of xi yi is less than equals to summation I equals to 1 to n mod of xi raised to the power p whole raised to the power 1 over p times summation I equals to 1 to n mod of yi whole raised to the power q, sorry, this raised to the power q and whole raised to the power 1 over q, p and q being conjugate number, p and q being conjugate exponents. Clear? P and q being conjugate exponents. Okay. Now let us see the proof of it. Okay, you can also define the Holder's inequality using the norm form rather you can say. So the Holder's inequality is norm form. So see, this is basically norm of xy, the first norm of xy, and others are the peak norms. Okay. These are the norm forms of the Holder's inequality. Now let us prove the Minkowski inequality, which will eventually lead us to the concept of Rn with a defined norm, as we have already defined it, to be a non-linear space, then eventually being a metric space. Okay, so we go on to the next page. Yeah, so proof of Young's inequality. Proof of Young's inequality. So suppose P equals Q equals to symmetric conjugate exponents. So in this case it is pretty trivial. Okay, that is AB is less than equals to A square plus B square quadratic mean. Whatever. So this is very trivial. Now if we are not taking the case of symmetric conjugate, then what we need to do is see. We first choose a function. Suppose, so the idea will be elementary calculus. Very simple. Suppose we have a function with independent variable t and it is defined as 1 over q plus t over p minus t to the power 1 over p. Okay, where this t is a real number. Okay, now what will be the first derivative? So it is sort of 1 over p minus 1 over p t to the power 1 over p minus 1. Okay, and see, in this case we have two things, that is, or rather we can say we have three things, that is, so this f dash t will be equals to 0 if p equals to 1. See, if p equals to 1, so this becomes 0. Okay, so it is greater than 0 if, let's say, t is greater than 1, and it's less than 0 if t is less than 1, provided p is less than, provided p is less than, clear? Provided p is less than. Okay, clear? Since we are defining these things for t and we are taking an arbitrary case where p is not 1, because we have already proved the trivial cases for p equals to 1, let us not define it as p equals to 1. Let us define it as t equals to 1. Yeah, so the same thing will happen. Now, so this definition basically gives us the following thing. See, so if we somewhat plot this function and say this is t equals to 1, so it touches t equals to 1 at the x-axis, And when t is less than 1, it's a decreasing function, and when t is greater than 1, it's an increasing function. So the graph might be somewhat like this. Let's see. And from this we can obviously say that the function is always greater than 0. So for all t belongs to R, ft is a non-negative function. Okay? The non-negative function. Now for this function we take a special case with t being a to the power p over b to the power q. Okay? So ft eventually becomes f of a to the power p over b to the power q, and which is basically 1 over q plus a to the power p over p times b to the power q minus a divided by b over q by p, and it will be greater than equals to 0 because this function obeys this condition. You can frame this on your own, putting t equals to a to the power p over b to the power q. Okay, so now we can write it like this: 1 over q plus a to the power p over p times b to the power q is greater than equals to a over b times q by, right? Is it clear? Okay. Now see, we are moving on to the next page. Now see, we have this definition, right? 1 over p plus 1 over q equals to 1. From here we can say p plus q equals to pq, right? So if we divide by p, what we can write? We can write 1 plus q over p is equals to q. Or rather we can say q over p is same as q minus 1, right? So we can use this in the previous statement. So we have got 1 over q plus a to the power p over p times b to the power q is greater than equals to a upon b to the power q minus 1, putting this, and then multiplying both the sides with b to the power q, we have b to the power q over q plus a to the power p over p is greater than equals to a over b to the power minus 1, that is 8. Thus you have the Young's inequality. You have the Young's inequality. And we use this Young's inequality itself to prove the Holder's inequality. Okay? It's pretty arbitrary. So let's prove it. And then we will be moving on to the Minkowski inequality. So let's see. So the Holder's inequality. Holder's inequality. So suppose we take 2 points from the Rn, n-dimensional real space, or rather we do one thing. Okay, rather we do one thing. See, the Holder's inequality is basically this one, right? Less than equals to norm of x to the power p times norm of, sorry, not x to the power p, norm of p norm of x times p norm of. Okay. So what we do is that we choose this to be alpha and this to be beta. Sorry, this is q. Okay. So we choose p norm of x, which is defined as summation I equals to 1 to n mod of xi to the power p whole to the power 1 over p equals to alpha, and norm of y to the p norm of y, which is given as summation I equals to 1 to n mod of yi to the power p whole to the to the power q whole to the power 1 over q equals to beta. Okay. The previous step, did I write the Holder's inequality correctly? Yeah. So we take it as alpha and we take it as beta. Okay. Now, a very trivial case of this inequality, that is when equality appears. Okay. So that is for, say, let's say alpha equals to 0, or let's say beta equals to 0. Okay. So in these two cases we have the equality. We have the equality. Okay. But what if they both are positive? What if they both are positive? So so let alpha be greater than 0, and let's say beta be greater than 0. Okay. So what we will basically prove is that summation I equals to 1 to n mod of xi yi over alpha beta is less than equals to 1, which will eventually give us the Holder's inequality. What we do is that we have already assumed alpha and beta. So we take a equals to, let a equals to mod of xi over alpha and b equals to mod of yi over beta in the Young's inequality. In the Young's inequality. So we have AB less than equals to a to the power p over p plus b to the power q over q, and we can write it like this: mod of xi to the power p over p times alpha to the power p plus mod of yi to the power p over q times beta to the power p is greater than equals to mod of xy times mod of yi over alpha beta. Right? Right. Now we can use summation on both the sides. Right? We can use summation on both the sides. So taking summation on both the sides, we have, so summation mod of xi yi can be written as mod of xi times yi equals to 1 to n over alpha beta. So this is less than equals to, okay, so I'm writing this first. It is less than equals to summation of this whole, and we can separate it, right? So we can separate it to write it as I equals to 1 to n xi to the power p over p times alpha b plus summation I equals to 1 to n yi to the power qi had here, right? Qi had, right? So to the power q over q times beta q. Okay. And since these two are positive terms, positive sums, since we have taken modulus, so this is obviously less than equals to 1 over p plus 1 over q, and 1 over p plus 1 over q is, so from here we can write summation I equals to 1 to n summation xi yi is less than equals to alpha beta, and we have already known the values of alpha beta, which gives us the Holder's. Okay. So let this lecture be up till this much. In the next lecture, I am gonna prove the Minkowski inequality, and then we will be moving on to the sequence spaces and so on. Okay. We will also define the same concept for the n-dimensional complex field. Then we will be moving on to the functional space. We have much discussion regarding these things. So we will be discussing the rest of the things in the next lecture. Okay.